Moving on to our next example, we have y double prime plus y is equal to 2t when t is between 0 and 1, and then equal to 2 when t is greater than or equal to 1. So what we have is a forcing term that starts at 0 and builds linearly to 2 over the time period from t between 0 and 1, and then it remains at 2 going forward. So instead of a forcing term that's initially its full strength of 2, we have a forcing term that builds from 0 to 2 linearly and then is 2 after time t equals 1. So we need to rewrite that forcing term again using Heaviside functions. So it starts as 2t, but then what we're going to do is we're going to turn off the function 2t starting at t equals 1. And instead, we're going to turn on the forcing function just 2 at t equals 1. Now, if we do some factoring, we can see that this is 2t and then minus 2 times t minus 1 times the Heaviside function at t equals 1. And so by rewriting the right-hand side like this, then we can start looking at taking Laplace transforms of the right-hand side. Okay, so let's take Laplace transforms of this differential equation. We're going to do s squared times the Laplace transform of y minus sy of 0 minus y prime of 0. That expression, of course, is the Laplace transform of y double prime plus the Laplace transform of y. And then let's take the Laplace transform of the right-hand side. The Laplace transform of 2t is 2 times 1 over s squared. And then we're going to take the Laplace transform of 2t minus 1 times h of t minus 1. So that's going to be a 2. And then the Laplace transform of t would be 1 over s squared. So the Laplace transform of t minus 1 times h of t minus 1 is going to be e to the minus s times 1 over s squared. So here, let's be careful to point out that the 1 over s squared part, that's just the Laplace transform of t. Okay, but then when I'm looking at the whole thing here, e to the minus s, 1 over s squared, that's the Laplace transform of t minus 1 times h of t minus 1. Now, I'm going to plug in the initial conditions. We made them both 0 so that this system is really only responding now to the forcing term. It's not having a response to the initial conditions. And so we're going to get s squared plus 1 times y is going to equal 2 times 1 minus e to the minus s over s squared. So that tells me that capital Y in this case, if I divide, is 2 times 1 minus e to the minus s over s squared times s squared plus 1. And so I'm going to rewrite this as 2 times 1 minus e to the minus s times a over s squared plus b over s squared plus 1. Now, you might be saying, why am I not saying that this is a plus bs and then maybe cs plus d? But because there are no terms that have a single s in it, I know that I can write this as a over s squared plus b over s squared plus 1 when I do the partial fractions. If you used a more general form with maybe a bs and then maybe a c plus ds on the other term, then eventually the coefficients of s would end up being 0. So I'm just going to use a slight shortcut here. A times then s squared plus 1 plus b times s squared has to then equal 1. So the coefficients of s squared tell me that a plus b would have to equal 0 because there are no s squared terms. Okay, but then a is all by itself as a coefficient of 1, so a must equal 1, and then of course that tells me that b must be minus 1. So in this case, we can get that capital Y of s is going to equal 2 times 1 minus e to the minus s over s squared minus 2 times 1 minus e to the minus s over s squared plus 1. So what is y of t? So I'm going to start with just the 2 over s squared. The inverse Laplace transform of 2 over s squared is just 2t. And then I'm going to subtract. Now I'm going to have 2 e to the minus s over s squared. Okay, so I just did 2s, or 2 over s squared. Now I'm going to do 2 over s squared times e to the minus s. So I basically, the e to the minus s is going to give me a t minus 1 everywhere I saw a t. So I'm going to get 2 times t minus 1. And then the e to the minus s is also going to give me a heaviside function of t minus 1. Okay, now I'm going to do essentially 2 over s squared plus 1. So that's 2 times 1 over s squared plus 1. So here, that's going to give me minus 2 times the inverse Laplace transform of 1 over s squared plus 1 is just sine of t. And then just like last time, I'm going to have a 2 times the e to the minus s over s squared plus 1. And so essentially, I'm taking the inverse Laplace transform of the same function, 2 over s squared plus 1, but now I have this e to the minus s that's in there. So that's going to give me, notice that I have a minus sign there and a minus sign there. So that's going to give me a plus. And I'm going to get 2 sine of t, but not sine of t because I have an e to the minus s there. That's sine of t minus 1. And then heaviside of t minus 1. So if I like, I can write this as 2t minus 2 sine t. And that's essentially the response to my forcing function of 2t. And then now I'm going to level it off, the forcing function. So I'm going to subtract 2 of h of t minus 1 times what seems to be left is a t minus 1 minus sine of t minus 1. And it's just nice sometimes to write your solution to one of these second order differential equations so that you have the parts that don't have a heaviside function in them and then the parts that do have a heaviside function in them. So let's see what the graph looks like of this solution. So here was my forcing term, 2x minus 2x minus 1 times h of x minus 1. Again, I'm using x's here for Desmos. Okay, so you can see my forcing function grows until t equals 1 and then is constant. And then this is what the solution looks like. And it's a little harder to see here, but hopefully you can see that the solution starts at 0 and then it increases. And notice that this oscillation never comes back to 0. So my forcing term of 2 has shifted that oscillation above the x-axis in this case.